Yes, Chitra ma'am, ready to go.
Yes, let's start with our today's session. A very happy evening to one and all present here. The secret of getting ahead is getting started. With this quote, in this warm evening, to refresh and create an impact onto the minds, Department of Electronics and Communication Engineering, Savita Engineering College, brings to you a webinar on text detection in natural images by Dr. Alex Noel Joseph Raj, Professor, Key Laboratory of Digital Signal and Image Processing of Guangdong Province, Department of Electronics Engineering, College of Engineering, Shantou University, Shantou, China. A glimpse of our college and department. Savita Engineering College, established in the year 2001, an autonomous institution which follows the Finland-based education model, and we march towards less is more concept. Our college makes the students job ready by providing Industry 4.0 ready curriculum which imparts the 21st century skills. Project-based learning integrated with subjects improves the student's skill set and makes our learners to be the best, which is the motto of our college. The Department of ECE was established in the year 2001. Our vision is to develop the department into a state of art with center of excellence in electronics and communication engineering education on par with global standards. The Department of ECE has well experienced faculty of proven ability and diverse specialization. The faculty actively involve themselves in research in the fields of robotics, VLSI, MEMS, image processing, and embedded systems. I would now like to introduce the guest of our day. Dr. Alex Noel Joseph Raj received his PhD degree in engineering from the University of Warwick, Coventry, UK in 2009, the master's degree in applied electronics from Anna University in 2005, and the bachelor's degree in electrical engineering from Madras University, India in 2001. From October 2009 to September 2011, he was with Vailport Limited, Tunis, UK as design engineer. From March 2013 to March 2017, he was with the Department of Embedded Technology, School of Electronics Engineering, VIT University, Vellore, India, as a professor. Since March 2017, he is with Key Laboratory of Digital Signal and Image Processing of Guangdong Province, Department of Electronic Engineering, College of Engineering, Shantou University, China. He is specialized in image processing with industrial and teaching experience in machine learning, signal and medical image processing, and FPGA implementations. We are very happy to have you with us today, sir. You may please take over the session now.
Okay. Thank you very much. Yeah. Let me take over the screen. Yeah. Okay. So, very good afternoon to all the participants. So, I'm Dr. Alex Noel Joseph. So, I'm a professor at the Shantou University, China. So, the topic for today is text detection in natural scene images. This is going to be the topic for today, and I'll be working on or explaining some of my algorithms where I apply this on natural images. So the word natural images means any image which is not constrained by any kind of lighting. So any image that is taken on from a camera, which has got some brightness controls, it doesn't have those kind of problems. An image taken from a mobile phone. So these images are called as natural images. And I'm going to tell about an algorithm where we apply that algorithm on these images to detect text. Okay. The quick introduction about me. So I got a PhD from Warwick, Coventry. So all this information I've been told by the host. So I also work on biometric shape reconstruction, text detection from arbitrary images, and I'm not audible. Okay, let me increase. Oops. Am I audible?
Yes, sir, you are. You can continue, sir.
I think somebody just messaged me. I'm not audible. Yeah. So text detection from arbitrary images, UAV localization, so, and medical images, especially on ultrasound image segmentations and 3D reconstructions. So these are some of my areas. And the other key local area I work on is called the FPGA, so field programmable gate arrays. So I try to implement imaging algorithms at real times. So this is also one of my core research work as well. So okay. So the contents of this presentation. So I will start with a very brief introduction about neural networks. That's what I will start off with. So I will try to explain them about the neural networks here. Then I will speak about the feature descriptors. So the neural networks require some kind of inputs, and you call them as features. So I used to work on a feature extractor called Zernike movements for a long time. So I will be explaining that. So how to use Zernike movements for text recognitions. And then I'll be explaining it from a detection point of view. So how to use Zernike movements for detection and localization of text in natural images. So this is how the contents of the presentation will go ahead. Okay. So this is going to be a very simple neural network. So you probably might have seen this. You've got an input layer, input layer, and output layer. So these 1, 2, 3, 4 are called as neurons. So you get inputs here. The inputs go to a couple of these layers, and you have some weights which get trained up. So as you give the inputs, which are basically features, the network gets trained and trained and trained, and ultimately it comes to a generalization. So once it is generalized, you send in a query. A query is basically an unknown image, and you expect some kind of output from that. Say, for example, in this case, okay. So in this case, you have an input here, and you have a network here. So earlier, you have trained this network to detect whether it is car or not car. And in the query image, what you do is you give an unknown image, and you expect the network to tell you whether it is car or not car. So that's how it happens. Okay. So now, just getting back to the neural network. So the neural network has got these layers. So one is called the input layer. So the input layer accepts what is called as feature vectors. So you have loads of feature vectors. So feature vectors are basically inputs here, and they are given with the class label. So the class label is nothing but a ground truth. Okay, we can call them as ground truths. And
Excuse me, sir.
Yes, ma'am.
Sir, actually, your voice is breaking, sir. I think your internet is a bit unstable.
Is it? Wait a second, ma'am.
Yes, sir.
Do you want me to check it again?
Yes, sir. Kindly reach. It is actually good, but suddenly the voice is breaking.
Oh my God. Okay, let me check again. Okay, let me go back. I think I got a proper one here. Yeah, mine is full, ma'am.
Okay,
Maybe,
but
maybe shall we switch off your, can you switch off your video and try, sir? That works sometime.
Okay. Okay, fine. I'll
Sometime
switch off
that
my
works.
videos here.
Only audio also works.
Okay, I'm switching off the video. Yeah, can you see it now?
yes, sir. Screen is visible.
Yeah. Okay. So basically, the input layer accepts features as well as ground truths, and you give these two to the input of the neural network, and the output layer computes a score, which means it gives you a decision. Okay. And the hidden layers, what they do is they keep on getting trained. You call them as training. So you just keep on getting trained, and they just generalize themselves. So how do they get trained is basically, it's got an algorithm called the backpropagation algorithm. So this algorithm propagates the error. So it sends back the error to the network. So the network tries to reduce the error between the desired output and the actual output. So when the error is within a particular criteria, you say the network has reached its performance goal. So once the network reaches its performance goal, you say the network has been generalized, and the network is ready to be tested for any unknown sample. So this is what a neural network actually does. Okay. So I've got something here. I don't know whether I can run it. Let me see if I can run this. Let me try. Probably no. Okay. So here you can see this one is a input. It goes into the first layer. Yeah. Let me see if I can do this here. Can I see the screen? Is it possible to see the screen?
No, sir, it's not visible actually.
Okay. Okay, I'm sorry. Now is it visible?
Yes, sir, it is. Yeah, it is visible, sir.
Okay. So if you see this, the network actually gets trained. So you can see it starts off with some kind of, a random number, and then slowly, the network starts to get into a generalized mode, which means it starts to get, see, now it has come into, the first layer has come into a kind of shape. Can you see it? It has generalized. So likewise, each and every layer gets into a kind of generalization. And once it generalizes, it stops. And that is where the error is minimum between the actual and the desire. Okay, so now let me go back to the main thing. Okay, and now I can share the screen. Now, can you see the screen now?
Yes, the screen is visible.
Okay, fine. So this is the concept of neural network. So neural network starts with a probabilistic, you got some inputs. The inputs are basically the feature vectors. I'll tell you what is this. So it goes into here. The network trains. The network trains and trains and trains. So you use an algorithm called the BPN, back propagation network, which means it propagates an error back to this network so that the error is minimized between the desire and the actual. And finally, once the network is you trained and you say the network is generalized. Okay. Now more about the neural networks. So can you understand this whole thing? So there is a network here, a neural network here. So the objective of the neural network is to detect whether it is car or not a car. So what you do is normally you give various images to the network. But in between the car and the network, there is somebody sitting here. This is called the process of feature extraction. So you don't directly give the inputs to the neural network. What you do is you try to extract features. Suppose you want to differentiate a car and a not a car. So what you do is the features could be like, you say the car has got 4 wheels. So you can say it has got 4 windows. Yeah, so these are features which are actually given to this network so that it can differentiate the car from a human being. For example, a human being has got 2 legs. Okay, so these are the differences. So you give these information to the network and you allow the network to train, and the network then analyzes it and says this is a car or not a car. Okay, fine. Now, there are so many features available in the literature, and you call these features as with a word called handcrafted. Okay, this is a very important word in machine learning and other kinds, So the word handcrafted means is you are the one who's picking up these features. So if your features are very good, then your network is very good. And there are some of the features here. So there are loads of features. I have listed out very few of them. Say, for example, bag of words, Fourier descriptors, gap out transforms. You got HOGs. These are called as HOG. Then you got scale invariant feature transforms. And this is a very important one called the DCT. Probably people into engineering will be knowing that. You got the discrete cosine transform, Array wavelets. There are so many transforms, and every day there are new and new transforms. And also, I told you these transforms are called as handcrafted, which means you are the one who's picking up these transforms. Okay. Now, these transforms, or we can call them as features as well, they are very effective in describing the image. So they should describe what it is. For example, if you want to say a car or a not car, So these features which you are taking has to describe the car. And the accuracy of the system depends on how well we obtain the features. If you are not able to get proper features out of the image, then your accuracy of the system just goes down. So the accuracy is very proportional or directly proportional to how well you extract the features. Okay. Now, how do we describe the features? Let us take, for example, the topic on feature description. So here I'm showing you elephants, and I'm asking you to describe this elephant. Okay. So what you say is, first you say is the color. So you look at the color. So one is the feature, one type of feature could be the color. So let us say color is one feature. Next, you can say the gigantism. So the height and the width. Probably you can call them as aspect ratio. Okay, so you can call this as aspect ratio. So it is much bigger than any human being. The third one is, you can call those legs, 4 legs, large ears. Yeah, you got some elephants have got large, huge ears. A tusk, they have tusks, they have trunks. So these are some of the features which you can just look at the elephant and say, okay, these, if I'm able to extract these informations from those images, I can definitely classify that image as an elephant. And as I told you, we try to extract as much information as possible to describe the object. And one of the most important description is the shape. So if you're able to extract the shape of an object, then you can extract, or you can actually provide more information about the object it is considering. So the shape is one of the biggest feature descriptor. Okay, so this is one of the biggest and most likely feature descriptor which you will be normally using in any neural networks. And I'm going to speak about today a shape descriptor which we can use it for text recognition. Okay. Now, I have been using Zernike movements. Okay, I'll tell you what is Zernike movements as we go through it. So this Zernike movements is a very useful shape descriptor which has been in literature for many years. Okay, so it was found by a physicist named Fritz Zernike. Okay, so he was also the inventor of the phase contrast microscopy. So he won the Nobel Prize for this. And where this Zernike movement was useful is, so they had a spherical lens. Okay, they had a lens from the manufacturing industry. So they had a lens being manufactured. And what they did is they wanted to find out the errors. Okay, so the manufacturing industry produces a lens, and they want to find out how good this manufactured lens is in according to the ideal one. So actually, they were trying to find out the aberrations in the lens from an ideal spherical shape. So actually, Zernike movements were giving us so much of information about the shape. So that's the reason they were being used in optical industry. And the second thing is about the Zernike movements is, you call them as orthogonal. Okay. So the word orthogonal refers to, suppose you have two different values. Say, let us say you got feature 1, feature 2, and you take the dot product of these features, it tends to be 0. What you can infer from this mathematics is, these two features are non-redundant. They have separate features and they are unique features which can give enough information. So feature 1 can give one information, feature 2 can give another information. So that is what they call as orthogonal. So if you have something which can give you a higher order error, so something which can give you a better information about the shape, and which can also give you non-redundant information, then one of the best feature that can use is the Zernike movements. So what happens is Zernike movements in image processing, people have started using it for shape recognition, face recognition, and so many other things. So in fact, people have used for biometrics. So you can use it for recognizing shapes, recognizing humans, you're recognizing different objects. People have been using it. And what we did is we tried to extract these Zernike movements and use them for text recognition. So if you want to know something about the theory, the mathematics about it, it's given here. So this is the image. So what you do is you just need to multiply it with a polynomial. Okay. So if you don't understand, just don't worry about it. I will explain you with some images. What is the advantage of this polynomial? So you got it's a second order, say for example, it's a two-dimensional polynomial. So you can see it has got n and m. And your image is also a two-dimensional, which is got f of x comma y. So you take this image and you multiply this polynomial. I will tell you the beauty of this particular n and m. Let us go to this one. Now, you got a small image here, a leaf. Okay. Now, I want to extract as much as information about this leaf, the shape information. Now, what I did is, you can slowly vary this m and n values. Say, for example, in this case, it is 1 and 1. And you try to vary this m and n over a range. For example, I varied it between 1, 1 and 14, 14. Okay. So what you can infer from this, as you increase the order, maybe you can say 1, 1, 2, 2, and you slowly increase it, you start to get more and more information about the object. Can you see it? Is it visible? Okay. So here, this is a very lower order polynomial. So this is a very lower order polynomial. But as you increase the order of the polynomial, what happens is you tend to get more and more information. And in this part, you start to get detailed information. So this is, you can call it as a global information. And at this point, you can call it as a detailed information. So this Zernike movements, with this polynomial, you tend to vary this n and m. And as you tend to vary this n and m, you try to get more and more details about a particular object. So if I just want to relate it to the shape, I could say, as I increase the order of the polynomial, I will get more information about the object. The more the information, it is easier to express it into the neural network, and the accuracy of the neural network improves. That's all the logic is. Okay. So this is the beauty about this polynomial called Zernike polynomial, and you can actually implement it and you can see it by yourself. Okay. So some of the facts about this Zernike polynomial, what it does, it provides shape. I told you this is a very good one, which can use it. You can use this Zernike polynomial, or you can say Zernike transform, or you can also say Zernike moments. So what this does is it gives you shape information. Then other good thing is it is invariant to rotation. Say for example, an object is there, say, and it is 0 degrees, and say for example, it gets rotated by 90 degrees. Both can be detected. Its invariant means the Zernike polynomial moment here and the Zernike moment here are the same. Okay, so it means they are rotationally invariant. The other thing is it's lower redundancy. In case you can say least redundant. So every feature has some information. Every feature gives you some unique information. So the more of the Zernike movements you take, more information you get, the more accurate the system becomes. The last one, which is very important, as I told about the Zernike polynomial. So the lower orders give you global shape, the higher orders give you detailed shape. So you can see it over here. The lower order gives you lesser information, but as you improve the order or increase the order, you get more detailed information. Now, coming back to the next part of our work, how do we use Zernike movements for text recognition? That's the second part. So till now, what did we cover? So till now, I will just put it here. So we saw about neural networks. So till this point. So I told you this neural network is something like this, and it requires features. Okay, and this gives you an output. Okay, and these features are very important ones. And I told you, if your features are not good, the accuracy of the neural network also goes down. And I explained to you about one thing called shape as a feature. And I told you shape is one of the most important features that you can use it for training a neural network. Then the third point I explained to you how to extract features, how to extract shape features. And I gave you an example of using Zernike polynomials. So in this case, I told you Zernike polynomial is a 2D polynomial. You got two values, m and n, or sorry, n and m. A smaller value of m and n will give you a global shape. So let me draw it here. So if your m is and n are smaller, you get a global shape, and your m and n are larger, you tend to get more detailed shape. Okay, so this is what we have been through for the last 20 minutes. Okay, so I gave you a basic idea about neural networks, features, shape as a feature. So how can we use, say, for example, a Zernike movement to get the features? Now, I'm going into the application. So now you might be knowing that, okay, all these things are there. So why? What is the application for this? Okay. So now I'm going to tell you about one of my research work of using Zernike movements for text detection in scene images. I will call them as scene images or natural scene images. Okay. So if you're interested in doing any kind of machine learning or any kind of image processing project, the first thing is you require images. You require lots of images. And one of those problems is sorted out with these natural scene images. So everybody must be having a mobile phone with a camera, and you might have taken so much of images about the surroundings, the environment. And you might have seen at least one of these images in your real life, Say, for example, you might have seen some backgrounds which have got some text here. This probably might be your test paper. And this is one which shows a direction. So there are so many images in your mobile phones which you could use it as inputs to train your neural network or your deep learning network. So you don't need to be worried about getting the data from somewhere else. That's one of the biggest advantage of working on natural images. The data is readily available. It's just your idea of using it towards it. So coming back here into the contents of this second work, what is the need to do text detection? Then I will be speaking about few existing techniques. Then I'll speak about my research work. How did I apply, how did I use Zernike movement in detecting this text? Some results, limitations, and I will also tell you what are the future directions in this particular research area. So let us start with this, need for text detection in natural scenes. So let me put this: internet is flooded images. I will also cut this and say your mobile phone as or is flooded with images. Okay, and all these images contain high level of information. Say, for example, I've taken some images here. So this one tells you, I don't know, it's called Panasonic. I don't know whether this brand is available still here. So it tells you this particular building has a company called Panasonic, a Qualcomm company, and it has also got a restaurant. This particular image gives you so much information. This one tells you to drop your waste. And this one is basically some kind of a direction, maybe a speed limit or a direction. Okay, and this is in Chinese. I don't know what it is. Suppose you have an automated algorithm which can recognize these texts, okay, and does some multilingual translation. For example, it tells me this one, I pass it to an algorithm, it detects it and tells me, okay, this is a direction information. Then this would solve most of the problem that is the real world is facing. So this was the biggest motivation for us. And you could say, okay, there are so many algorithms and you can say all these things. I'll tell you the challenges here and you will understand how difficult it is to work on these natural images. Okay. Now, here is an example of what you see in a text in a document and text in real life. So if you're somebody who wants a challenge, you can actually start to analyze this. The first one is, let us take this text in a document. You can see the document, the background is whitish, it has got a white frame on top of a black text. So the contrast is huge because you want to read the text. So obviously, when you write a text in a document, you have a huge contrast between the background and the foreground. The second thing is the fonts. Look at the fonts of these. All of them have the same fonts. And also, you are able to extractly remove each and every word. The spacings are same. The characters between each word is same. The font is same. And you can easily develop a simpler algorithm to extract each and every word and then apply it to a OCR. You call this as an optical character recognition. You can send each and every of these to the OCR, and from there you can infer what it is. This is something very, very simpler than what I'm speaking about in terms of natural images. Look at this one in terms of natural image. You can see, have a look here. Each one has its own complexity. So the first one, you can actually read the text because it is on a white background, but it is oriented. The orientation is not perfect. It is not exactly horizontal, or it is not exactly perpendicular to the camera angle. It has got an orientation. The second case, again, you can read this, but still you got various other objects here, and also it has got the orientation here. So here you can look here. The background and this one are almost similar. The text has also got a similar color as the background. And in this case, it's much more worse. There is a shadow. Take this image onto your rightmost, yeah, this one. You got a huge scene here, no text information here. A text is available only at this point. So now you can understand what is the challenge between a text in a document and text in a real life, or you can call them as natural scenes. So I just listed out some of the problems. One is they exhibit different colors, fonts, scales, orientations. Yeah. Then it has got interference from low resolution, occlusion, distortion, whatever you call. And you can also say text, like some of the text look like fence, bricks. Yeah, in this case, you can see here, this one and this one will always look the same. So this also looks like a T here. Some of the other objects in the background also look like text. So these are the biggest challenges that you can face across when you work on natural images. Okay. Now, Microsoft released a data set. This is what a challenge they released. So they released in 2012 a data set. So they took images from almost so many, 500 images they took across. And they released a challenge to everybody and said, can you do a text recognition? So this data set had got two things. One, it had got English language, and also they had Chinese language in that. Chinese, okay, Chinese language. So it had both in this. Okay, and your challenge is to detect the text. Okay, and people are taking it at a different perspective, different camera angle. They don't bother about it. So I will show you the text in this particular image. If you want to look at it, the text is somewhere on the top. It is over here. I can see it here. It's at this point here. So this was a challenge. So you don't find any text in this old region. You find text exactly at the top leftmost corner. And they asked us to find out, can you detect this text in this image? And they gave the ground truth as well. So if you want to work on this data set is publicly available. So if you want, you can actually work on this data set and try to develop an algorithm. Okay. So let me go into some of the existing techniques. So one is texture. Text. So if you have a background and if you have the text on the foreground, the text alphabet or the characters, they have a specific texture. So you can differentiate them. Second thing, all these texts will have a particular component. So you call this as connected components, which means the text will have some kind of regularity. So suppose I write A, B, C, D. All of them will have kind of, some kind of a regularity, which you can use it to find out them. Then the last one, which is more informative, you can see they use what is called a sliding window method. I will just explain this alone in the next slide. And you got an hybrid technique, which has got a combination of all these things. Okay, this is an example. I just put some examples here. You can see here. Texture means, as I told you, this has got a specific color. With respect to the background, you can use various image processing algorithms to detect them. And here you call this as edges. Edges is basically a change in gray level. So if I move from white to black, there is a change in gray level. You can extract the text based on that. And this is what called as a sliding window technique. So this is a very professional and very, very, a workable technique in real life. So what they did is they had a small window and they moved this window on the image. So this window has got 4 parts, the green, 2 green parts and 2 red parts. So whenever this window comes exactly on the text, you can see here, at this point, it comes exactly on the text. You find these 2 red regions, will be similar. Okay, when it comes exactly on the text, these 2 regions will become similar. And if you just take these 2 images, these 2 blocks, they will be dissimilar. Can you understand this? So you move this window, they call it as a window, which is slide on the image. So as they slide on the image on every particular row, they try to find out the similarity between these 2 regions and the dissimilarity between the red and the green. So similarity between red and dissimilarity between red and green. Whenever the similarity between red and red is more and the dissimilarity between red and green is less, they call them as text lines. Okay, this is what they do. They just move across. They take this window, so you can see it here. They move the window, and as they move the window on the image, when it exactly comes onto the text, these 2 will give a similarity score of almost 1, and the red and green will give a similarity score of say 0.2. So using this metric, they're able to find text lines. And this was a very wonderful algorithm because they achieved almost say 95% accuracy. Okay, that was a very huge algorithm, and they were able to get a huge accuracy with this particular algorithm. Okay. So if you look closely, there are certain problems with these techniques. So the first one, if the contrast is not good, the texture descriptors may fail. Objects in the scene which may having a fence and other things, they also fail on edge descriptors. And this technique, if you look closely, the sliding window technique, so you need to move each and every row. And basically, when you move each and every row, what happens is it is computationally intensive to detect the text. So it takes like, at least like a couple of hours to process one image and find the text in that particular image. Now, what is our goal? What is our approach? So our approach was, we took up 3 different things. One is, from this big image, what we can understand is the text is not present anywhere. It is just present at one particular corner. So we wanted to reduce the area of text analysis. So if I could remove these regions, which I call the background regions, and try to narrow down my region where to find the text, then probably I can have a better computationally faster algorithm. The second thing, what was my goal is, can I use some rotationally invariant, which means if the text is like this, if the text is like this, I should be able to recognize them. So I wanted to use some kind of rotationally invariant features to train my neural network. And then once I extract these features, I should be able to train a simple neural network, or you can call them as a simple classifier. People use the word classifier. And that particular classifier will say whether that region has got text or non-text. Okay, this was our idea. So first goal was, we wanted to reduce the area. We don't want to just work around regions which doesn't have any kind of text. Extract rotational invariant feature maps, which means even if the text is inclined oriented, I can extract the information. Then employ a simple classifier, say for example, a simple neural network to do the classification, say regions which have text, regions which don't have text. This was our idea. Okay. So how did we approach this? So if you note any of these text regions, you can see you got a background and you got a foreground. Okay, the text has got huge contrast between the background. So what you call is you can apply variance. So variance is nothing but the absolute of standard deviation. And standard deviation is nothing but the deviation from the mean. So any value which is deviating from the mean value of the pixels, I can classify them as text. Okay. And similarly, text regions, if you look here, all these them are having black color, or they have some kind of, constant texture. So entropy would be another thing which gives you information about the homogeneity. Homogeneity means a cluster which has got the same statistical value. Say, for example, clusters which have same pixel values, if I can put it like this. So we applied these two things. One is, the statistical variance filter and the entropy filter. And what we did is we took up values which are greater than the mean and values which are greater than greater than the median in both the cases. And then we just took intersection of these two things. So once we did it, you can see we can actually get closer to the text and we can remove the background. So the background is basically black, which means it's 0. So I don't need to work on this. So I can actually remove the background and I become very closer to the text. Just by very simple statistics like variance and entropies, we can actually remove the background and we can get closer to the text. But there is so I can show you some images here. Here you can see, in this case, you can see the text here. The usage of these two filters can give you the text and you can remove the background here. You can see that here. And some more results you can see. This particular image doesn't have, it's got a huge background, way less text here. So you can see we can eliminate these ones here and we can narrow down to the text. Similarly, text is only here, background eliminated in this case, narrow down to the text. And just by using a simple entropy and a variance, a combination of these two filters, you can remove as much as background information and you can narrow down yourself. Coming back here. So this doesn't look that easy. Say, for example, this is an image here. Again, this was given by the MSRA dataset, so Microsoft Research dataset. So in this case, the text is here. The background is there. Both are having almost the same color. The contrast is not that much. So if you apply any kind of statistics to this, you will end up like this. So the text becomes a part of your background. So this becomes a problem when you apply statistics. Okay, if you apply statistics, this becomes a problem. So what we did is we worked on an extension of this algorithm. So what we did is we apply this statistical filters. I think I told you this entropy and variance. We found out what are the regions that are available. So this is one text region, and this is a huge text region. We call this as the abnormal text regions. So what we did is we took these abnormal text regions and we did additional thing which is called as the pruning. So in pruning, what we mean by this, we try to remove this region and get closer to the text. That's what I mean by pruning. Pruning is basically cutting off certain unnecessary things. So that's what we named this additional algorithm as pruning. So for this, what we did is, it was very simple. We tried to detect closed contours because texts have got closed contours. Okay. So we try to apply some close contour techniques, then corner deduction. So we try to detect the corner of the text, draw some kind of, a line to this, and then find out the slope of these lines. And if the slope is within a particular threshold, we said that they belong to the text regions. So what we did is, first we took the subblocks, we divided them into normal subblocks and abnormal subblocks. For the abnormal subblocks, we applied pruning. So in the pruning thing, we started off with a closed contour, which means an edge which is going, which has got a closed contour. A closed contour is basically like this. It is continuous. So you call this as a closed contour. In the closed contour, we found out the corner points. So for each corner point, we drew, a line, took the slope of these lines, and found out which are the slopes they fall within a threshold. If they fall within a threshold, we call those regions as text lines. And then we eliminated the other background regions from here. And that way, we narrowed down the text regions from here. So from this case, what happens is we have regions, normal regions, abnormal regions, which have been pruned and text being detected. Okay, so this is the regions here. Okay, fine. So it serves two processes, the pruning. One is it localizes the text, in these abnormal regions. And we also further subdivide them. So you can just further subdivide these abnormal regions into smaller regions. So now, according to the algorithm, we have the following. So text regions, which are obtained directly from the statistical filters. That's one thing. The second one is text proposals or regions, you can call them as regions as well, that have been pruned, which means you got a huge region with a smaller text. We remove this and we locate them. This is called pruning. What we do is then with these regions and text proposals, we send them to the Zernike movements where we extract the shape features. Okay. And once we extract the shape features, we call them as shape descriptors. Okay. Fine. So this one I explained you. So in this case, f of x is basically going to be your text regions. So we got both the normal region, the pruned region, all these things comes here. You multiply them with this particular polynomial, this huge polynomial, you multiply them. And once you multiply them, you get something similar to this. This is an example of a Zernike feature map. Okay. So you can see here, the background, you don't get any information about the background because there is no shape involved in this background. But if you look closely, this has got some shape, and the Zernike descriptor provides this shape. Can you see it here? These regions do have some shape, and this is also visible here. But this is different from this shape. Different. So this is text, and this is non-text. So there's a huge difference between these two regions, text region and non-text region. So to still explain you, I've just taken out an example here and compared the features from the Zernike movements. You can say the features for text and non-text here. So for the first one, you can see, just give me a second, yeah. So here you can see, this is a non-text region. This is a text region. Both of them pass into the Zernike feature maps. And you can see non-text regions have got bigger magnitude of Zernikes, and text regions have got smaller magnitudes. And if you're able to draw a kind of a line, then you should be able to actually differentiate non-text and text regions very accurately from the Zernike descriptors. So keeping this in mind, what we did is for each box of text region, so we took so text region, non-text region, let us call text region and non-text region. All of these pass into a huge Zernike movements. We extracted loads of movements in that and we trained it. So this is the entire algorithm that we used. Okay. So I just explained most of this, and this is the part where I was explaining you earlier about the neural network. So first is being trained, and then a query comes in, and the query tells you 1 or 0 in this case. So we tested it on a bilingual data set, which means what I say is it has got both English and Chinese text. And this was released by Microsoft in 2012. So they use a benchmark score called the F-score. So this is something different from accuracy and probably used or mainly used in decision systems. So in decision systems, they don't use accuracy. They use F-score, sensitivity, specificity. So F-score is a kind of, a combination of both sensitivity and specificity, or you can say precision and recall. So we use that kind of, a score to give us the benchmark here. So the first one is, can we remove the area of text analysis? So in our case, we were able to save or eliminate the background to a extent of about 72% of the image was eliminated just by using the simple statistical filters. So we just used simple statistical filters, and we were able to eliminate the entire background, and we were able to get closer to the text. So this background was eliminated up to 75%. That's one of the analysis we did. The second one is, we call this as a confusion matrix. A confusion matrix tells you two things. That how good your text regions are being identified as text regions. How good your non-text regions are identified as non-text regions. Then here, these two things are important. Text being identified as non-text and non-text identified as text. So this is more important for your decision systems. So we analyzed this as well, and we came across an accuracy of about 98% with respect to training the neural network, which means you train the neural network and you give one of the training samples to test it. So that's called training. Then the testing part is with an unknown sample. So the unknown sample, we were getting about 95% accuracy, something called close to 96. So this is about the classifier performance. And the good thing about the research from the Microsoft is they give you the ground truth. The green ones are ground truth. So they ask people to actually put a bounding box on the text. Say, for example, the green one is what you're supposed to detect, and the red one is basically what we detected it. So we need to find out the area at which these bounding boxes overlap. So for example, in this case, the text is in an orientation, but our bounding box is just, it's perpendicular. So there is an additional area which has to be eliminated. So we have to calculate that as well. So we call this called as maximal suppression. So we did that as well. And with respect to the ground truth with the bounding box, we were able to get a precision recall. For the training set, it was like 77% and 64% with the F-score of 70. Then for the testing set, which is actually the unknown one, so we were able to get like about 65 to 67%. And we also compared it with other techniques, you can see here. So ours is something better than, the existing one in 2019. So ours was better than the other techniques for this particular data set. So something like 0.67, which was the best one in terms of the accuracy and the F score. Okay, fine. So this is some of the test results we had. The first one, okay, let me go through this one. This one is basically the ground truth. This is, if you just use MATLAB gives you a text detection algorithm. So you got a text detection algorithm in MATLAB. So you can look at that. You can just take the text detection algorithm in MATLAB and you can test one of these images. So MATLAB wasn't able to find out this. There is something written down here, but actually our algorithm was able to find out this one, which was something very good. So this is the ground truth. Maybe you can't see that, but MATLAB wasn't able to find out, but our algorithm was able to find out this. This is something very good from our algorithm purpose as well. Okay. Some more results. Okay. Here you can see text being detected. Even the text is blurrier, but still you can detect this. And here also you can detect the text. This is actually in an orientation. This is quite difficult. You are still able to detect it. And this is also one of the easy. I think this is the easiest one to detect. Yeah. Almost all algorithms will have their limitations, and even our algorithm will add some limitations. This is one of the worst images that we had in our data sets. The first one was, I don't know whether the Microsoft, you can see it here, but it is so reflective. So our algorithm wasn't able to detect it. This was unseenable. You can't see this at all, but still our algorithm didn't work. This, the contrast is very bad, and here the text is hidden inside, a background, kind of, you can see those things here. The text is inside this. Our algorithm failed to detect all these things. Okay, so I think I have come to my conclusion. I think I don't know how many hours I spent on this. Okay, probably an hour or something. So what we did here is, so I told you about a method which gives you a better accuracy, better F score. So I explained you about my algorithm, and I told you my algorithm employs a rotationally invariant moments. Basically, they are called as Zernike moments. Okay, so I told you what are the advantages of the Zernike moments and how they could be useful for text recognition, because they are shape descriptors and text are basically shapes. So you can use Zernike moments to extract them. And finally, I told you a much simpler way to remove the background. So you can remove the background. So in that case, we're able to remove the background up to 70%. And we can able to locate the text much more easier by just using simple statistics, for example, variance and entropy. So if you use a combination of statistics like variance, which tells you the deviation from the mean values, and entropy, which tells you the homogeneity of the surrounding pixels, if you can use those things, you can eliminate a background up to a 70%. So this is what I was wanting to explain here. And if you need more reference about this, so this got published in a very good journal, Intelligent Fuzzy Systems in 2019 with one of my students. So you can have a look at this paper. Or you can just go to my RG and you should be able to get some information about this paper as well. Okay. The last part of my research, okay, so I think many would be interested to knowing what could be the research directions from here. As I told you, text detection in natural scenes, you don't need to worry about the data set. The data set is available everywhere. You just require a simple camera phone. So this is one of the recent works where people wanted to detect curved text, which means you have to detect as close as possible to the orientation. It is not like drawing a box like this. You need to work this as close as possible. Oh, okay, sorry. Yeah. So you need to go as close as possible to the orientation of the text. That is one of the main requirements of this research work. So it says curved text detection and recognition. So I spoke only about detection, but there is a huge potential in terms of recognition, which is after detection, you try to extract it and pass it to the OCR. That's a bigger thing in the world. So in 2017, they produced a paper. I think it was in the Arabic. So you can look in for the new paper, which will be available. So they proposed a curved text detection algorithm as well as a data set. So you can look at that. And this is some of the images from their research work. So you can see how other algorithms are working and how well their algorithm is working. So this is one of the research directions. The second research direction is 3D text. So I did some work on this. I had a conference paper on this one. So nowadays, if you just go down to any nameplate or something like that, or a name board, they don't use 2D text. They use 3D text. So this is an example here. And if you want to recognize this one using any normal OCR, it's impossible. The normal OCR are not feasible to recognize 3D text. So what we did is we developed an algorithm where we try to remove the depth as well as the shadow. So here you can see here, we removed the depth and the shadow, and we converted the 3D text to 2D text. And then we were able to recognize each and every character of this. This is also one of my works. So it's I think I submitted for a conference. You can look here. So once you remove the depth as well as the shadow of this, then you should be able to use any normal OCR to recognize the text here. So this is also another research direction. You can look into that. These are some of the data sets which we took across. So all these data sets, we took it by ourselves. So we just went out, we took a photograph of this, we used it. So you can see here, TVS, fashion, all these things, it's all our data sets. So as I told you, if you want to work on this natural images, you don't require huge amount of investment. All you require is your mobile phone and your algorithm. Fine. So further, you can work on multilingual text detection and recognition. So I worked on bilingual. You can go for multilingual. For example, you can work on Arabic letters, Tamil characters. Hindi, so many things are available. You can just work on. So once you detect the text, you can also go in for recognition. So recognition is basically how close you can use this OCR to get some information from the text you have been detected. And this is another one which I was telling you, the curved text or text with different orientations. You got text like this, something text will have some different orientations like this, text will have different orientations. You should be able to work on this, and then you should be able to get so much of data from just by using your mobile phones. With this, I think I spent like oddly more than an hour, I think, be continuously speaking. So I would like to thank you guys to giving me an opportunity to speak to you. And you can contact me on this particular email ID, jalexnoel@stu.edu.cn. And I'll just take a couple of minutes to just tell about my university. So I work with this university called Shantou University in China. So it's in the southmost part of China called the Guangdong province. So I work under this group called the Pattern Recognition and Machine Intelligence Group. So this is the aerial view of your university. You can see this. It's a very beautiful university. Yeah. So so we have two different groups, one which works on medical images, another one which works on natural images like text images, biomedical text images, you can say machine images. So we got a small group, and we regularly take in students to work with us as interns. So this guy was the guy who worked with me in this text recognition. This is another guys who worked with me, who come from India, and they work with me for a couple of months. And we develop an algorithm and we write papers based on this. And this is the hospital which we communicate. So we use quite a lot of medical images to develop algorithms as well. And some of the pictures where students from VITs and NITs came and worked with us. And I also work on medical image segmentations, breast cancer recognitions, detection, diagnosis, I work on those. And we also work on deep learning. So one of my research areas is also on deep learning. So if you want to look, and you can look at this particular aspect. So RDA unit. So you can search this one on the internet. So we have developed a specific deep learning algorithm to detect breast lesion segmentations. So this one segments those lesions very accurately. Okay. So with this, and we also work on tumor detections. Yeah. So all these are additional things for you. So my motive was to speak about text recognition, explain you about the neural networks, explain you about the feature extraction techniques, and that's it. Okay, thank you very much for your patient listening. I think I took too much of your time, and I think I end my presentation here. So if you want to ask me any questions, feel free to ask me now, because I can see quite a lot of people raising their hands. Yeah, you can just ask me now. I just over to the host now.
Yes, sir. Thank you very much, sir. That was really a wonderful session. And we convey our heartfelt thanks to you for sharing your valuable knowledge with us.
Okay.
Yes, sir. So we've got a few questions from our participants.
So should I stop the share? Okay, shall I stop the share?
That's fine, sir. This can be we'll proceed with the question, sir.
Okay, go ahead.
Yeah. The first question that you've got, can ZM be used for retinal image detection?
Come again, what was it?
Can ZM be used for retinal image detection?
Absolutely. Yes. Feature. So you can look into one of my papers on, so you can just look into Zernike moments are basically shape descriptors. Let me put it like this. Zernike moments are basically shape descriptors. So if you want to detect any shape, you can use Zernike moments. So I have used this one to do retinal segmentation. Okay, so you can look into my PLOS one paper. Okay, so we have used Zernike moments to do retinal segmentation. Yes, absolutely possible. Yeah.
Yes, sir. Thank you very much. The next question that we have, what algorithm can be used to extract information from an image that is 80% vague in nature?
80% of
blurred, like vague.
Vague.
Yeah, VAGU. Yes, sir.
What does it mean?
Like a blurred image, which is not much clear.
Okay, a blurred image. So
yes.
So I think the first step is you need to remove the blurriness. So you have to go to the enhancement process. So you need to remove this blurriness, right? Well, I think the question is like, it doesn't, I just need some more information. So blurriness is one aspect of image processing. So you need to enhance the image to remove the blurriness. So blurriness is nothing but a low pass filtering, correct? So let me put it like this. So you take an image f of x comma y, you convolve it with g of x comma y. So this is basically, let us call this as a Gaussian filter. Okay, this is basically a low pass filter. And this will give you a blurred image. Okay, so the first step to remove is is to remove this blurriness by applying some kind of enhancement technique. So you have to use some kind of enhancement technique like Wiener filtering or something like that to remove this blurriness. So once you remove the blurriness, you have much more details in that image, which you can use it for extraction. So you can say, for example, once you remove the blurriness, the details will be highlighted. That's what I meant. Okay. So once the details have been highlighted, you can use that image to do whatever you want. I think it's an open-ended question, I would say.
Okay, sir.
Are you able to follow? It's a very open-ended
Yes,
question.
yes, sir. Yes,
So
yes.
what you want to do with the blurred image is up to you. Are you going to work with the blurred image? Are you going to enhance with the blurred image? It's just up to you. So first step is enhancing the process. Once you get the enhanced image, which is nothing but high-pass filtering or adding high-pass information. So once then you get the details, and from the details you can get some more information you want. Okay. What is the next question? Yeah.
Thank you very much, sir. The next question that we have, can you tell us the difference between machine learning and deep learning algorithms?
Okay, very good question. Okay. Okay, say for example, okay, so this is your neural network, and I drove the car here. Okay. And I told you some person has to sit down here and he has to do the feature extraction process. So he has to extract the features here and train the neural network. So this is basically a machine learning concept. Okay, or you can just, so you need to extract the features. Deep learning is you got to have images, you send the images here. The deep learning has got feature extraction process. So this contains the feature extraction process in itself, and it also has a classification process. The classification process is nothing but your neural network. So your deep learning, machine learning is basically feature extraction has to be done by someone, and this feature extraction has to be passed through into a neural network. Deep learning, it is a huge thing. All you need to pass is images. The CNN, they call it as a convolutional neural network. It has got two parts. One is the feature extraction part and the classification part. This classification part is nothing but a fully connected neural network. Okay. So this is the difference. In deep learning, you don't need bother about this feature extraction process. You just give images. In machine learning, you require features, you extract the features, and you train the neural network. And the accuracy of the neural network depends on how well you extract the features. Am I clear?
Yes, sir. Great, sir. Thank you very much. The next question that we have, why is there a variation in detailing of the images as the order of M and N increases?
Okay. Why is the order? Okay. Okay, fine. So, okay. So Zernike movements N and M. Okay. So if I just draw a sine wave, okay. Okay. So let this sine wave call N is equal to 1, M is equal to 1. Now I try to increase it. So when I say N is equal to 2 and M is equal to 1, what happens? You tend to have more zero crossings. So what by this zero crossing is, I can establish more edges. So the more I increase the order, the more zero crossings I get, which means I get more edges. More edges means more information. That's the reason if you just look here, let us go back here. Let me go back to that particular image here. Yeah. So if you look here, this one, maybe the width of the sine wave could be a low pass one. But here you have more sharper or higher frequency sine waves or higher frequency polynomials. So as the order of the polynomial increases, the frequency of the zero crossings increases. And if the zero crossing increases, what happens? You get more and more edges. So if edges are more, which means you have more information and more details. It's very simple. So you take a canny edge detection filter and a robots filter. Canny has got more edges, okay? Because it works by, it looks into the standard deviation as well as, it looks into so many, it applies a low pass filter and then looks into the standard deviation. Similarly here, as you increase the order of the filter, you get more and more zero crossings, and these zero crossings give you more information, which is basically very relevant for, for any kind of shape extractor. Am I clear?
Yes, sir. Great, sir.
Yeah. Any questions more?
Yes, sir. One last question.
Mm-hmm.
Do we use any signals for detecting the shapes in medical field?
Signals.
Yes, sir.
Medical field means?
Have you said image detection now? Do we have any reference signals for detecting the shapes?
See, shape is basically a two-dimension, right? See, are they speaking about images?
Images, sir. Yes.
So do they have reference images?
Do we use any input signal as a reference to detect the images in the medical field? To detect the shapes and all that.
Okay, say for example, see, if they're speaking in terms of signals, then they are speaking in terms of 1D. If they speak about images, then they speak about 2D, which is basically shape. Correct?
Yes.
Say, for example, if you want references, and you get references means I believe they are speaking in terms of ground truth. If they are speaking in terms of ground truth, there are so many things about it. So ground truth, there are so many data sets. So I normally go in for one that is called as Kaggle. Kaggle.com. I don't know how many of you know this. So if you want to have any kind of data sets, I just first refer this particular website called Kaggle. Kaggle.com. If you just go down here and you can do a quick search about the various data sets, so you get ground truths for training and testing as well in some cases. So I would first go into this one to look for any kind of, say, for example, if I'm going to work on signals, if I'm going to work on images, I just go into Kaggle first, search for data sets. If the data set is available, I use them. In most cases, you get the code as well. Kaggle is basically a competition website where people use some people, upload their data sets and they allow others to test their algorithm. So in most cases, you get your codes as well. You can get some codes and you can start working from there. So ground truths are definitely available for both medical data sets in terms of signals and images as well. Yeah.
Yes, sir. We've actually got two more questions recently, sir. Can we take them up?
Yeah, go ahead. Yeah.
Yes, sir. One question is, can ZM be used in video analytics or only in static images?
What is video? Video is f of x comma t, correct? So obviously, what you're going to do is, even if you have a kind of, a processing element, let me call this as a processing element, you are just passing f of x comma y in terms of time. So at each time instance, only one frame goes in, and this frame is basically an image, correct? So let me put it like this. So this is, unless you have processing elements in parallel, so let me draw it like this. So there are processing elements P1, let me say P1 up to Pn. N is basic PET, let me put it at PET. T is the number of frames, okay? So at a time instance, you're processing only one frame, and that frame is basically f of x comma y, which is basically an image. Zernike movements are useful for shape detectors. As long as your idea is to detect a shape, then you can use it. In terms of videos, yes, absolutely, because you're not using, a video is basically a continuous set of frames. And at each point of instance, you're going to use only one frame. That is basically an image. So definitely you can use Zernike moments in videos considered as a frames. Yeah.
Yes, sir. Great. And the last question for this session, sir. What are the latest image data sets compared to AlexNet, GoogleNet, etc.? And can you explain about reinforcement learning?
I haven't worked on reinforcement learning. I'm sorry. My knowledge about reinforcement learning is very limited. Okay. So you said I can speak about AlexNet. Okay. So this is basically you got then you got VGG 16, 19. I've used it. So these are basically CNNs, which means you got convolutional layer. Then you got convolutions, I think ReLU and max pooling, correct? So you have these three things, and what you do is you have a series of these placed like this, and you get a deep network here. Deep network. So similarly, VGG 16 and 19 have got like so many layers. So VGG 16 has got 16 layers, 19 has got 19 layers, I guess. Okay. Then you have something called ResNet. Okay. So the ResNet is basically what happens is you got your convolution, you got your ReLU, you got your max pooling. Then what you do is you take the input image and you add it along with this, and then you pass it to the next group. Okay, so this is ResNet. So you call it residual net. So you call this as the residual network. Okay. So the reason why they are doing this is they are solving what is called as vanishing gradient problem. Earlier, they had a principle that when you have deep networks, which means many layers, improves the accuracy. That's what people add in notion. But what happened is, as you increase the layers, the error was not propagating backwards because the error was very minimum and the system was not training. When the system is not training, it means it gets saturated. There's no need. So, and this, adding more layers to the network doesn't make any sense. So then they understood that if you can add this X to this part here, then obviously you can solve the vanishing gradient problem. So you got AlexNet, PGG, ResNet, then you got UNet. UNet is got, you got both, it has got a shape of a U, which has got encoder and decoder architecture. So this is basically used for segmentation. You got variants of units, many variants of units, something which has got dilation, convolution, attention gates, then attention gates plus dilation, convolution. So there are so many variants. This is all I know, and I have done some work on units, especially with dilation, convolution, and attention gates. I have done some work, so I am actually know that. Then you have GANs. Yeah, GANs, you got a differentiator and a generator. So it has got two modules in that. So we have used it for segmentation. These are all things I have worked on. So I haven't worked on reinforcement trading. I'm sorry about it. Yeah. Any questions?
Thank you very much, sir. That's it we have for the questions today.
Okay.
Shiba ma'am.
Yeah, ma'am. Thank you. I would like to thank our sir. He has got wonderful knowledge. He has published various research papers in very high impact factor journals. He's got wonderful publication to his credit. And today in this session, even though he is a wonderful researcher, he explained very clearly the very difficult topics. He explained very clearly to our students in a very simple manner. So I would like to thank him for the wonderful time that he has spared with us. Thank you for sparing your precious time with us, sir. Thank you so much,
very
sir.
much. Yeah.
Over to Chitrama.
Thank you very much, sir. That was really a wonderful session, and we had a knowledgeful session, in fact. Thank you very much, sir.
Okay, thank you very much. Yeah.
Yes, sir.
Okay, ma'am. Thank you. Yeah, thank you. Bye-bye.
Bye, sir. Thank you.
Bye, sir. Thank you, sir.
Bye, ma'am. Yeah.
We thank all the participants for joining with us today. Hope you'd have enjoyed the session well and all the questions have been answered by our speaker. I would like to announce about our upcoming webinar. Our upcoming webinar is on Power of You by Ms. Jayashree Rajendran, internationally certified corporate and NLP trainer. She's also a public speaker, writer, and blogger from Dubai, UAE, scheduled on July 8th between 4 p.m. and 5 p.m. I request all the faculties and students to attend the webinar and get benefited. Meet you all in the next session of our webinar series. The feedback link will be posted in the chat box soon. It will be posted in the chat box for Zoom as well as the YouTube live streaming page. We request all the participants to fill up the feedback form with the correct email ID. The e-certificates will be sent to you within 2 days after the completion of the webinar. I repeat once again, the e-certificates will be sent to your email IDs after 2 days, within 2 days after completion of the webinar. So we kindly request you to fill up the feedback form with the correct email IDs. And we request the participants to fill up the feedback form within 10 minutes after the session gets over. We would like to inform that this feedback link will not be shared through WhatsApp or through email. Thank you all for your participation. Stay safe.
Sir, perfect, sir. Actually, இல்ல நிஜமாவே நான் என்ன நினைச்சேன்
Announcement about our upcoming webinar. Our upcoming webinar is on Power of You by Ms. Jayashree Rajendran, internationally certified corporate and NLP trainer. She's also a public speaker, writer, and blogger from Dubai, UAE, which is scheduled on July 8th between 4 p.m. and 5 p.m. I request all the faculties and students to attend the webinar and get benefited. The feedback link has been posted in the chat box. The e-certificates will be sent to your email within 2 days after the completion of the webinar. Thank you.